Good morning. I am Dr. Thushari, chemical pathologist from Teaching Hospital Ratnapura. Today my talk is on overcoming interferences in spectrophotometric assays. This is my overview, basics of spectrophotometry, interferences including spectral and chemical, and errors in spectrophotometric measurements. As you all know, a spectrophotometer is an instrument which measures analyte in a solution qualitatively or quantitatively. It's the most flexible, reliable, and commonly used instrument in clinical chemistry. Every chemical compound absorbs or transmits or reflects lights over a certain range of wavelength. When we consider light, it has a certain amount of energy which is inversely proportional to its wavelength. So, shorter wavelengths carry more energy and longer wavelengths carry less energy. Specific amount of energy is needed to promote electrons in a substance to a higher energy state, and it is detected as absorbance. Electrons in different bonding environments in a substance require a different specific amount of energy to promote the electrons to a higher energy state. That is why the absorbance of light occurs for different wavelengths in different substances. So, in spectrophotometry, we use the method that each compound absorb or transmit lights over a certain range of wavelength. It's a method to measure how much a chemical substance can absorb light by measuring the intensity of light as a beam of light passes through sample solution. So there are two types of spectrophotometers depending on the range of wavelength of the light source. First one, UV and visible range spectrophotometer, which uses light over the ultraviolet range, that means 185 to 400 nanometers, and visible range for 400 to 700 nanometers of spectrum. Other one is the infrared spectrophotometer, which uses light over the infrared region. That means 700 to 1500 nanometer of spectrum. These are the components of spectrophotometer, which consist of light source, lenses, wavelength selector, slit, sample solution, photodetector, signal processing, and result output. So as I showed in previous slide, components of spectrophotometers, the following are essential components in a typical spectrophotometer. Source of radiant energy and monochromator for the selection of a narrow band of radiant energy, an optical system, detecting system, and a readout system or a display. When we consider spectrophotometer, we should know the transmittance and absorbance. Transmittance is the fraction of light that passes through the sample, and it can be calculated using the following equation. Transmittance is equal to the light intensity after the beam of light passes through the quiet divided by the light intensity before the beam of light passes through the quiet. So the amount of photons that goes through the quid and into the detector is dependent on the length of the quid and the concentration of the sample. Transmittance is related to absorbance. Absorbance is equal to negative logarithm of the transmittance. So here in spectrophotometer, we use Beer-Lambert law. But this can only be applied when there is a linear relationship between the absorbance and the concentration of the sample. Here, we measure the absorbance. We should know the molar concentration of the analyte in the sample. And we can calculate the concentration of the analyte in the sample. When we consider interferences, it's occurred in vitro interferences. These are occurred due to matrix effects. It contains chemical compounds in body fluids which can react with reagents, and they can mimic physical, chromatographic, immunological and spectral properties of the desired analytes. When we consider interferences in spectrophotometry, we can divide it into two: spectral and chemical interferences. The most common spectral interferences are hemolysis, lipemia, and icterus. Spectral interferences occur when a compound causes a response in spectrophotometer similar to analyte what we are going to measure. Simple and most common interference is the interference by hemoglobin, which occur in many analytical procedures. Now we consider how hemoglobin interfere in assays. Absorbance of oxyhemoglobin is in the range of 500 to 600 nanometer in visible spectrum, and if any analyte use this range in their measurement, it can have interference. Example I'm going to talk about here is the measurement of total protein by biuret reaction. Here in the first graph, it's uh, it depicts absorbance of oxyhemoglobin. It can you can see that wavelength from 500 to 600 nanometers. There's maximum absorbance. In this graph, we can see the absorbance of a protein standard which measured at the 540 nanometers. In the dark line, it indicated absorbance of the protein standard 50 milligram per liter only. In the dotted graph, it indicates standard plus hemoglobin, which cause positive interference in the protein assay. Now, we are talking about turbidity. Turbidity is caused by VLD molecules in the sample, and it causes incident light to scatter, decrease the transmittance of light, and result in high absorbance values. The best method to avoid this is sample dilution, but the dilution is limited by the ability of analytical procedure to measure the analyte. Sample blank and kinetic measurements are not working properly when sample is lipemic or icteric because of errors occur due to high absorbance. When we consider spectral interferences, we should know how to correct it. These are the simple four methods which can use for the correction of spectral interferences: sample blank, kinetic measurement, bichromatic analysis, and dilution. Sample blank. We use sample blank to minimize the spectral interference. Sample blank is sample plus diluent instead of reagent. When we do the correction for spectral interference, we have to measure both absorbance of complete reaction mixture and absorbance of the blank. Then we subtract absorption of blank from absorption of complete reaction mixture. It works only if the interference is not present in gross amount. If interference is present in gross amount, it causes large errors. This method can eliminate color inherent to the sample. We use reagent blank to eliminate the color inherent to the reagent. When we consider reactions, endpoint reaction, it is monitored at single point when the reaction is almost completed. In endpoint reactions, if there's no interference, reaction curve should go through the origin. But if there's interference is present, curve is parallel to the original curve with bias. Now we talk about kinetic measurements. Absorbance of colorimetric reaction we measure against the time. Absorbance is measured at two different time points with final color development has not occurred and response versus time remains linear. And absorbance include both original endogenous color and color formed by analytical reaction. These are two graphs. First, we look into this graph. It indicates time versus absorbance for the colorimetric reaction. As you can see, when they are standard alone, that curve goes through the origin, and if there's interference, the curve not goes through the origin, but it parallel to the standard curve. When we see that 1 and 2 points, you can see time versus absorbance is linear, but point 3, that time it's not linear. Here we can see the concentration versus delta absorbance. Here both standard alone or standard with interference both goes through the origin. Here we can see time versus absorbance for the creatinine. This is for the creatinine, and these are the which are slow reactants, and this is for the fast reactants. If we take readings during this time period, we can avoid slow reacting and fast reacting interferences mostly. So here is a time versus absorbance complex reaction of mixture containing fast reacting and slow reacting interference plus creatinine. As you can see here, it's only give absorbance by fast reacting components. Then this is by creatinine and fast reacting. This is by fast reacting, total creatinine and slow reacting one. So if we take measurement during this period, we can avoid the interference. Delta absorbance is the absorbance first reading minus second reading. It's the specific color formed by the analytical reaction. So when we prepare standard curves of kinetic analysis, we use delta absorbance versus time. It is itself a self-blanking method, and there's no need of separate blanks. Now, I talk about bichromatic analysis. It's the simultaneous measurement of absorbance of reaction mixture at two different wavelengths. It includes primary wavelength and another wavelength, secondary wavelength close to the primary one. Here's a graph which you can see there are two wavelengths. This is the primary, this is the secondary wavelength. In primary wavelength, we get the observed absorbance because of the chromophore and black. And here in secondary wavelength, we get the absorbance due to interference. Although compound may give a spectral interference, absorbance maxima of interference differ from that of the analytical reaction. So it is assumed that absorbance caused by interference is approximately same at primary and secondary wavelength. We prepare standard curves based on absorbance at primary and wavelength minus secondary wavelength, or absorbance at primary wavelength divided by secondary wavelength. We can use Allen correction. Allen correction we use to correct the background interference. Here we measure absorbance at primary wavelength and additional two wavelengths at equidistance from peak, and average of absorbance of last two wavelengths. It's the average of background absorbance. But this is valid only if the background absorbance is approximately linear with the wavelength over the region in which the measurements are taken. Here's the graph. If we take measurement at 300 nanometer wavelength, then spectral curve for the chromatophore and interference. This is the solid line. It indicates both. And background interference is the here, that dotted line. When we take average of absorbance at 280 and 320, it represents background interference at absorbance maxima of 300 nanometers. So if we get absorbance at 300 nanometer corrected equal to absorbance at 300 minus absorbance at 280 plus absorbance at 200, 320 divided by 2. But you have to remember improper use of Allen correction with nonlinear background interference can lead to large errors. Allen correction is effective in minimizing effect of interference by bilirubin and turbidity in direct spectrophotometric analysis of serum hemoglobin. And we can use dilution, which can reduce the interference, but we have to be careful not to over dilute the sample. When we talk about chemical interference, chemical interferences react with reagents in analytical reaction. So it can be a positive interference or a negative interference. For correction of chemical interferences, we can use dilution and increasing the specificity of the reaction, removing of the interferent, monitoring of the assay by kinetic reaction, or monitoring the assay by bichromatic reaction. These are some example for the method which we get chemical interferences. When we measure glucose by Benedict method, we can get interference, positive interference from uric acid, creatinine, protein and glutathione. In oxidase peroxidase reaction, it causes bilirubin and ascorbic acid cause negative interference, where uric acid cause positive interference. Glucose oxidase and oxygen consumption method, hemoglobin cause negative interference and ascorbic acid cause positive interference. Hexokinase method, fructose cause positive interference. As previous one in creatinine assay, Chafe reaction, ascorbic acid, glucose, protein and ketones cause positive interference. If we measure VMA also in two different methods, here I have mentioned, it also cause positive interferences. How do we remove or eliminate these interferences? We can do dilution of the sample, but this is effective only in cases of interference do not react at the same rate or produce same color intensity as the analyte. We can increase the specificity of the reaction using specific enzymes as reagent. Examples are glucose by hexokinase or glucose oxidase method and uric acid by uricase method, urea by urease method. We can separate analyte from the interferent. We can get that by precipitation, filtration or centrifugation caused to protein-free sample, and we can do liquid-liquid extraction where analyte and interferents are separated into two different liquid phases, and adsorption or partition chromatography as well. We can use kinetic reaction. Interference react at different rates from the analyte. Example is the Jaffe kinetic reaction for the creatinine. So then I'm going to talk about errors in spectrophotometry. Errors in spectrophotometry occur. Two types of errors occur. It's occur due to mathematical relationship between the absorption and absorbance and percentage of transmitters and limitations of the instrument. When we talk about absorbance variance, there is a logarithmic relationship between the percentage of light transmitters which we measure and absorbance which we calculate. So at very low percentages of transmittance, small changes in percentage of transmittance result in large changes in absorbance. Example is Change of percentage transmittance from 60 to 50% produces absorbance change of 0.08. But when there's a percentage transmittance change from 15 to 5, it produces absorbance change of 0.65. So, small changes at very low percentages of transmittance produces disproportionately large changes in calculated absorbance and cause large errors in analysis at this part of the scale. Errors of the spectrophotometric measurement can be considered as a function of full or total scale deflection of the detection meter or its electronics. When absorbance scale is set at 0 or transmittance scale is adjusted to 100%, we can get the maximum electronic signal. For error analysis, variation in transmittant percentage of transmittance is perceived to be constant throughout all readings in the scale. Because percentage of transmitters directly reflect the electrical signal, we can do some simple calculation using percentage transmitters. Here, if we consider 1% variation in percentage transmitters at full scale, there's an error of plus or minus 1% transmitters. Half scale, it goes plus or minus 2% transmitters of error. And at 10% of variation, it goes plus or minus 10% of transmittance variation. However, percentage of transmittance is not directly proportionate to the concentration of analyte. Absorbance is the one directly proportionate to the concentration. So, we have to convert percentage of transmittance to absorbance and then calculate the error according to this scale given here. Here, we can see absorbance according to that. We can get absorbance according to the percentage transmittance according to this scale. Here's the table which indicate absorbance error as a function of percentage transmittance. Conversion of percentage of transmittance to absorbance in a logarithmic fashion. So at both ends of the absorbance scale, which means low absorbance, it means 0, and high absorbance, when absorbance is more than 1, have greatest errors. It means when a solution contains little color, it is difficult to differentiate between no color and some color. At high absorbance, it's not easy to record accurately a small amount of light passing through the solution. So, spectrophotometric measurement should be taken at absorbance between zero point 0.1 and 1.1 to minimize this error. This is the curve which indicate relative absorbance versus percentage of transmittance. So you can see here the relative error is minimum at the percentage of transmittance of 36.8 and absorbance 0.434. Now I'm going to talk about instrument limitation. At 100% transmittance or zero absorbance, all the light signal is converted to an electrical signal. If we consider the signal measures 1000 nanoamperes, when absorbance change by 0.01, there is a decrease in signal to 990 nanoamperes. So, instrument must measure accurately 10 out of 1000 nanoamperes or 1% change in the signal. To do this accurately, instrument must measure signal to plus zero point 0.1 nanoampere or 1% of 10. So at zero absence, there is at zero absorbance, there is a difficulty of accurate measurement of signal. If absorbance is 2, signal to photomultiplier is only 10 nanoamperes. because only 1% of the light reaches the photodetector. To achieve same degree of accuracy between values of absorbance 2 and 2.02, the instrument must measure the difference between 10 and 9.9 amperes or zero point 0.1 nanoamperes. To do this accurately, it must measure signal within 0.001 nanoamperes or 1% of zero point 0.1 ampere. So, at high absorbances, limitations are caused by inability of the detection system to accurately measure small differences between high levels of absorbance. When we are analyzing a relatively high levels of absorbing compound or interferent, a large spectrophotometric error will occur. To avoid this, we can do initial dilution to lower the absorbance and addition of a sample blank. Thank you. Uh, if you have any questions regarding my presentation, you can email me. I will personally respond to you. This is my references, Theory Analysis Correlation, 5th edition of the Kaplan. Thank you very much. This is my email address.